Alrighty, this is the chemistry of caramelization by Daniel Meyer. So caramelization is a non-enzymic browning reaction. Why might we caramelize things, you ask? Well, caramelization can cause desirable changes in food flavor as well as color. So here by this time you might know the answer, or you might be asking what can actually go through caramelization. Well, sugars can go through caramelization. Specifically, glucose, fructose, galactose, and sucrose. Maltose would also be on this list, but I only went over these four. So glucose is a monosaccharide, and its initial temperature of caramelization is 160 degrees Celsius, and its composition is right there. Fructose, another monosaccharide. Its initial temperature where caramelization begins is 110 degrees Celsius, significantly lower than that of the other sugars. Galactose, initial temperature of caramelization is 160 degrees Celsius. And sucrose, the example I will be using for this presentation, is 160 degrees Celsius. And as you know, sucrose is made from, composed of glucose and fructose bonded together. So how does caramelization happen? Caramelization is caused by the dry heating of molecules of those sugars. So in the beginning of this caramelization process, water is removed. Melting the sugar, such as sucrose, at a high temperature leads to boiling. The water is removed from the sugar and it splits this disaccharide into a monosaccharide, specifically glucose and fructose. Which makes sense if you think about the composition of sugars being hydrogen, oxygen, and carbon. Basically, through this heating process, what will happen is more and more water is removed and being created into basically water vapor. Oxygen and hydrogen will be lost in this process, leaving us with more carbon. So the condensation step of this is where the individual sugars, since we have monosaccharides now, lose more water and begin to react with each other. There are many ways in which they can do this. And one example of this is difructose anhydride, as shown here. Isomerization is the next process, which is where one molecule transforms into another molecule with the same atoms, but different arrangements. The heating of the sugar molecules continues. This as well as more dehydration reactions. So an example would be like aldose and ketose. And since molecules move faster at higher temperatures, which we all know, this also plays a role in a plethora of reactions that occur. The kinetic energy of these molecules increase, so they're kind of running around slamming into one another. More water is lost or produced as vapor, as mentioned before. That will happen through this whole heating process. So fragmentation and polymerization are the last series of reactions in caramelization. So what happens in fragmentation, you might ask? Fragmentation, the sugars now having gone through chemical processes now go from molecules the size of like aldose and ketose that we showed before, and begin to fragment further. This is where our flavors are produced. The bigger molecules get reduced to smaller molecules and become even smaller molecules. There are hundreds of these flavors that are produced. Polymerization is where even smaller molecules, in quotations, called monomers come together to produce chains of polymers. This is also where our color is produced. So polymeric caramels are used in like commercial production of food all the time, and we can categorize these into three different categories: caramelons, caramelins, and caramelins. They have a very high molecular weight, as you can see there. So a couple examples. Like I said, there's tons of molecules that are produced as a result of caramelization. So the heavier molecular weight products of the caramelization process are used for coloring, as mentioned before, because those are our colors. We use them in like colas, sodas, soy sauce, ice cream. We really use them in a ton of stuff. These commercial caramels are often produced by heating sugar in the presence of other cofactors rather than just heating sucrose, as we used as an example. Um, Two of these cofactors could be like ammonia or a sulfite, in order to produce different like variances in the colors or charged caramellins or caramellins. Um, this can be important as if you're using a caramel color in soft drinks, it must be negatively charged so as to prevent reaction with the phosphates, which would basically eliminate the color and be absolutely pointless. Diacetyl is an important compound that's produced during the early stages of caramelization. This is one of those flavors we mentioned earlier, and is responsible for a buttery or butterscotch flavor. It's also produced by bacteria in fermented products such as beer, which is kind of cool. Furans like HMF and HAF found in honey to cigarettes. Really, it's found in a ton of stuff. Milk is also included in that list, which was fairly odd. Acetic acid can be a compound that is produced during the caramelization process, which can produce a sour flavor, or we know that acids can produce an astringency to food. Esters, which provide a fruity flavor or aroma, and maltol, which we use as a bread additive all the time because it has a bread-like flavor, and we use it as like a flavor enhancer to make bread more bready. With that, I will show you guys my references, which the first and foremost and by far the most useful was foodinfo.net. This website is Wageningen University. Yeah, anyway, it's in the Netherlands. It's a very helpful website on food science. And this video, this YouTube video, which was produced by Harvard, which I deemed was a credible source of information. Anyway, that is the chemistry of caramelization. Tons of products, tons of applications, and this is a molecular reaction. I just want to emphasize that it's not the same thing as like ice melting into water, for instance, because that is a reversible reaction, whereas caramelization is not. Anyway, have a good day, and thank you for listening to my voice.